Okay then, we're here with another specified practical, and this one is on hard water. So Mr. Mulroy is going to run us through. I'm just going to run us through the equipment here. I've got a stopwatch, I've got a measuring cylinder, I've got 4 samples of water, okay, of different hardness. We've got some soap solution and a pipette. Let's see what we're going to do with this. I'm excited.
Okay, so in this practical today, we are going to be testing the hardness of these 4 samples. Okay, so I've got sample 1, 2, 3, and 4. I do not know, and I really want to stress this, I don't know which one is hard, which one is soft. I also am not sure which one is permanent and temporary hardness. Now, before the beginning of this video, I've used a measuring cylinder to put exactly 10 centimeters cubed of water into that test tube. And now let's begin the prac. Okay, first just want to talk to you about our table of results. So I've got sample 1, 2, 3, and 4, and you can see them there. I've got the volume of soap before boiling and the volume of soap after boiling. Now, step number 1, first thing I'm going to do is I'm going to use my pipette, and sir, if you want to zoom right in, there's a little 1 milliliter mark on there. I'm going to use my pipette to add 1 milliliter of soap solution. Okay, I'm going to keep the same soap solution for every single sample. Okay, very careful. Now this is a bit of an inaccuracy, so if you want to come and zoom in again, you can see it's actually quite hard to see whether I've got exactly 1 milliliter. Okay, so rather than a drop-in pipette, I could perhaps use a graduated pipette. So I'm going to add 1 milliliter of soap in there.
And what would a graduated pipette do better?
A graduate pipette would mean that I can control the volume from the start. So rather than it being a bit of human error and guesswork, I can control the volume.
So we've got 1 centimeter cubed in there now.
I'm then going to use my stopwatch, and I'm going to shake this for exactly 5 seconds. And I'm going to be careful to make sure I'm shaking the same speed and same up and down motion. Okay, so ready? In 3, 2, 1, go.
And what time? 5 seconds.
So that's 5 seconds. Now, what I am looking for, I am recording how much soap is required to form a lather. Okay, we can see a lather is bubbles. I haven't got any bubbles in there at the moment. So I'm now going to have to add more soap.
So the effect you get from running a nice bubbly bath.
Yes, I'm looking for that bubbly bath. And we're looking for one that lasts, okay, for around 30 seconds. I'm going to time it, but I'm looking for one which is 30 seconds. So I've got another milliliter of soap here.
So I guess we've got to keep track on that now. If you was doing this with a partner, they would be maybe keeping a tally by here of how many milliliters are being used.
So I've put 2 in so far. That's it. Make sure my bung is safely on top. And again, I'm going to shake for 5 seconds. And if you notice, I'm at the same speed as before. Stop. And then again.
Oops, sorry.
We haven't got our lather yet, so I'm just going to repeat the process.
Until you get one.
Until we get one. So
okay, so we'll revisit this when we actually get a lather. Otherwise, this video is going to be too long. Results now, we could see on the time lapse then the bubbles have gone down slightly because it's taken us quite a while to get the sample D lather, but that was this is what we're looking for, that sort of bubbly effect there. So let's come up with a table of results. You can see that sample 1 had 3 milliliters or centimeters cubed, 2, 5 and 2. So which one in your opinion now, sir, was the hardest of the waters?
I would say 3, sir.
Is that because it took more, a bigger volume, I should say, of soap to cause bubbles?
Yes, so the more bubble or more soap we need to make bubbles, the harder the water. That's one of our disadvantages. So I'd then say sample 1 would then be the second hardest because it took 3 centimeters cubed, and then finally 2 and 4 are around the same hardness. They're the softer watertight because they don't take much water.
Okay, so before we talk about accuracies and things like that, so what's this final column for?
So for this final column, so far I've worked out which ones are hard and which ones are not. Okay, so I found out that 3, we've still got a lather. It took me ages to get this lather, is the hardest because it required the most soap. But I'm not sure whether that hardness is permanent or temporary hardness. Now, to get between the two and work out whether I've got permanent or temporary, I'm then going to go ahead and boil all 4 of these samples. Okay. If the number of soap goes down at all for any of them, that means that it contains some temporary hardness, because boiling will remove that form of hardness. Any permanent hard water will not be affected. Okay, we can only remove that either using washing soda or what we call an ion exchange column.
Okay. Well, just in terms then, how can I make this experiment? I mean, you mentioned some inaccuracies about measuring the volume of soap, which we've only got that sort of standard pipette. You mentioned another type of pipette, which was...
So we would use what we call a graduated pipette. Okay, so that would allow me, rather than having to make sure on my own that I get 1 centimetre, I would then be able to pre-program it so I get exactly 1 centimetre cubed every single trial. I'm getting the same amount of soap. So that would be our first major inaccuracy.
So I've seen some videos in science labs where the shaking method is done by a machine. Do you think that would be also another improvement method, that rather than you shaking, because you're shaking at maybe different speeds that you can't
Definitely,
control?
sir. Towards the end, my arm got a bit tired. I mean, time lapse, you probably can't see that. So maybe at the start, I was shaking quite hard and quite fast, whereas towards the end, perhaps I got a little bit tired. So what I would use is a shaking machine. We could use a simple shaking vibrating machine, or I could use what we call a magnetic stirrer. Okay, so I would put a little magnetic bead in here, and that bead would spin around, shaking it up at the same speed all the time. So I'm never getting different amounts.
Brilliant, brilliant.
So the one thing I would say about the stock clock is we've got a really good resolution. So we're going to 2 decimal places. The only thing I would say, and I'll sort of model this now, is that human error comes in where I'm not sure we're able to stop it exactly on 5 seconds every time. But if we were using technology, what we would do is have that computer linked up. Just say we've got a magnetic stirring bead that would be linked up to a computer, and it would stop exactly on 5 seconds every time. So
I suppose you could program the shaking machine to stop.
Yes.
So that's the sort of thing. Anything else we're missing here, sir, that they might ask us about? Maybe repeatability?
So repeatability, first thing you can see, I've only done this once. Okay, so I've got a set of results. At the moment, they're not repeatable. I would need to do this experiment again on my own. So I would do exactly the same method using the same equipment and see if I get the same results. If I wanted to see if they were reproducible, I would perhaps get yourself or Miss Lahan or Miss Hillsden to do it, and then we would sit down and compare those results. And if those results are similar, we can say that the data is reproducible.
Oh, very good. And just finally now, let's talk about variables. What was the control variables, sir? What were the things that we needed to control in order to get a valid set of results here?
So the first, well, we've got quite a few control variables here. If we remember right to the start, I put 10 centimetres cubed
Easy for you to say,
water
sir.
in each one. I used exactly the same soap throughout the experiment. Example 1, 2, 3, and 4 all had the same brand of soap. Each time, I shook it for 5 seconds, okay, and I controlled that by using a stopwatch. I only ever added 1 centimetre cubed of soap solution, and I controlled that using a pipette. And I know we've spoken about it in terms of inaccuracy, but the control variable was the speed and hardness of my shaking method, and I tried to control that myself. In terms of independent variable, so the thing we are changing was my 4 samples of water. And my dependent variable, the thing I was measuring, was the volume of soap required to form bubbles, or, posh scientific word, a lather.
And I guess it comes back to the first column is always our independent, and our second column is always dependent. And if I was to graph this, this would be my x-axis and this would be my y-axis. And it very rarely changes, especially at this level. So one nice little tip just to leave you there, and enjoy the exam, guys.